This is problem number 4 for our Review Chapter 9 problem set. In the year 2000, the average duration of phone calls originating in one area code were 9.4 minutes. The telephone company wants to perform a hypothesis test to determine whether the average duration of phone calls has changed. They randomly sampled 50 calls originating in that area code and found that the mean duration of these calls was 8.6 minutes. Do the data provide sufficient evidence to conclude that the mean call duration has actually changed from the 9.4 minutes in 2000? Perform the appropriate hypothesis test using a significance level of 1% and assume that sigma, or the population standard deviation, is 4.8 minutes. We're going to use a p-value approach to do this particular test. We're going to show the 6 steps, formulas, variables, and you can use a picture if you want to help you get the correct p-value, but it's not required. And at the end, we will state the strength of our evidence, and that's going to be based on the size of our p-value. So for any hypothesis test, we're going to need 6 steps. Since this is a p-value test, okay, the first 3 steps are the same as when you do a critical value approach. We'll state our hypothesis, the significance level, get the test value or the test statistic. But now the 4th step is going to be the p-value. That's going to come from the test statistic. And then in the 5th step, we'll use that p-value to decide if we're going to reject or not. In step 6, we will interpret the results. So to do these steps, we're going to need a few variables to help us out. So first of all, the sample mean. If you look in the paragraph here, they tell you that from the 50 calls that they tested or sampled, they got a sample mean of 8.6 minutes, so that's the sample mean. The mean we're testing against is the 9.4 minutes. And the significance level is 1%. Remember, 1% is 0 or 1, 0.01. And then the standard deviation, it's a population standard deviation, it's a sigma, and that's 4.8. So these are the variables we'll use to do our steps. And let's just jump right in. Step number 1, we're going to state our hypotheses. And the null hypothesis is always that the mean equals some established value, and in this case it's 9.4 minutes. The alternative is either going to be greater than, less than, or not equal to. So we look back at the problem definition here, and they're interested in if that mean has changed. So that's going to be a not equal to. So greater than or less than, it's a two-tailed situation. Okay, and then the significance level, as stated, is 1%. Step 3, so we did 1, 2. Step 3, we want to get our test statistic or our test value. So we need to take the sample mean and convert that to a z-value. So we'll call that our z-test. And we're going to use the equation from Chapter 9 from that, just converting x bar to a z-value. Okay, and that is on our equation sheet. So now we plug in the numbers for that. Sample mean is 8.6, established mean 9.4, standard deviation 4.8, and the sample size is 50. All right, so plugging those numbers into your calculator, working carefully, you should get negative 1.18. This is our test statistic, or our test value. And from this value, we're going to figure out the p-value. Now, the p-value is the probability of our test statistic, or in this case, because it's two-tailed, it's actually going to be twice the probability of our test statistic, because we want to be able to compare the total p-value to alpha. And if, in this case, the test statistic, the probability of the test statistic alone is only going to be half of what we need. So if we draw the graph here, if we put 1.18 in here, all right, this will be the probability of, kind of half of it here. This will give us the probability of our test stat if we look that up. Since it's two-tailed, we're going to multiply that by 2 and compare it to alpha. Otherwise, we would have to compare it to alpha over 2. The other way you can look at it is you can remember two-tailed. You can just take your test statistic and plot it on here, almost like take the absolute value of it, and you plot the negative on the negative side, positive on the positive side of z, and you think of your p-value as the total of these two here, which of course they'd be the same. So your total p-value will be twice the probability of your test statistic. So if we find the probability of negative 1.19, so we just look this guy up here, we'll find out that it is 0.1190. All right, so the total p-value, when we multiply that by 2, is going to be 0.2380. That's a pretty big number for a p-value. Okay, so that's saying that 23.8% or almost 24% of the time this thing could randomly happen. That kind of sounds like random variation to me. So let's see what happens when we do our comparison, the final test here, step 5. When you're doing a p-value test, the p-value hypothesis test, the test you want to do in step 5 is you want to say if your p-value is less than or equal to alpha, that means you got something very rare or very unusual. That's the case where you're going to reject the null because your test data seems really out of place, so you're going to reject the null. Got something that's very rare. Or if your p-value is greater than your alpha or your significance level, you're going to say that that's normal variation, so I'm not going to reject my null. And that looks like that's the case I think we have now, because we look at our p-value here, we get 0.2380. We're testing against a significance level up here of 1%, right, 0.01. And certainly 2380 is a lot bigger than 0.1. So this is, this is not a case where we're going to reject. This is going to be a do not reject situation. We're not going to reject the null, which means we're, do not use your alternative. Okay, because it seems like from this test data that we got that this test set looks like normal variation. It's not something that's unusual. So we would not reject the null. So that's kind of our short answer right there. So now let's go ahead and interpret that. You always start out, when you do your full interpretation here, you always start out with the significance level. So we will say at the 1% significance level, the data do not or does not, it does not provide enough evidence to reject the null. Evidence to reject the null or the null hypothesis. So if we're not rejecting the null, that means we cannot say the alternative. So we cannot say the mean, and let's remember what were we testing here? I believe it was calling times, mean call duration. So we cannot say the mean duration of calls has changed from 9.4, and that was from the year 2000, and I think it was 9.4 minutes. Okay. So at the 1% significance level, the data do not provide enough evidence to reject the null hypothesis. We cannot say the mean duration of calls has changed from 9.4 minutes. So then the very last part, we want to state the strength of our evidence. Obviously, we don't have a lot of evidence here since we didn't reject, and certainly the p-value tells us that. So you would say strength, the strength of evidence to reject, is weak to none, since the p-value is greater than 10%. Greater than 10% or 0.10. So anytime your p-value is greater than 0.10, that means you have a weak to none evidence for rejection, which is why